Okay, let's dive right in. Today we're looking at a completely radical design for a brain-computer interface. And look, we're not talking about replacing human intelligence. Forget that. We're talking about a speed of light upgrade, an architecture that suggests the human mind doesn't need to be replaced, it just needs a much, much faster tool.
And that really gets to the core engineering problem, doesn't it? Most of the BCI tech you hear about is focused on access speed, basically helping us type faster with our thoughts. But that doesn't fundamentally expand our capacity to think. Sure, it gives you a quicker on-ramp, but it doesn't make the engine itself any more powerful.
The real issue is this fundamental bottleneck, the analog to digital conversion. You see, the brain's processing is massively parallel. It's analog, it's rich. But current BCIs try to force all of that richness through a tiny serial digital pipeline. It's like trying to stream an 8K movie through an old dial-up modem. The Neurophotonic Engine C, or NPA, architecture just sidesteps that problem entirely. It's a biological synthetic hybrid that's designed to connect the brain's raw intent directly to a passive optical system that literally operates at the speed of light.
But hang on. Before you can even think about connecting a light-speed accelerator to the brain, you've got a massive signal-to-noise problem. I mean, your brain is firing constantly, right? You can't have every random thought spike triggering the system. So the very first piece of the puzzle is this incredibly elegant chemical gate.
So let's just walk through how this biological lock and key works. When you have a high-agency, deliberate thought, not just background noise, it triggers a localized release of the neurotransmitter glutamate. The surface of the device is coated with an enzyme that reacts specifically with that glutamate, and the byproduct of that reaction is hydrogen peroxide. That H2O2 is the chemical trigger. It's the key that turns the switch and ensures only a genuine, validated intent actually gets through. And what's really fascinating about this slide is seeing how those chemical steps are actually built into a physical device. You can see the whole stack here. You've got the biological environment at the top, this encapsulation shield in the middle, and then the active switch at the bottom. The chemical signal gets converted into an electrical one, which then, in turn, opens the gate for the optical output. Okay, the material science here, this is where the design gets really clever. The active switch is a lead-free tin perovskite, so it's safe for the body. Now, this material is notoriously sensitive to oxidation. That's normally a huge weakness. But here, they've repurposed that instability and turned it into the core switching feature. The hydrogen peroxide oxidizes the perovskite, and that's what flips it on. To protect it from everything else, there's a 50-nanometer glass skin of alumina that seals the device off from body fluids but is still engineered to let the peroxide create that field effect. It's brilliant. So the gates open, and the signal triggers a photon emission. And this is where we leave the biological front end and get to the main event, the optical accelerator. This is a processor built not from silicon, but from light itself. The speed here is genuinely difficult to comprehend. We're talking about 10 femtoseconds. That's 10 quadrillions of a second. To put that into perspective for you, in the time it takes a beam of light to cross this tiny 2-millimeter crystal, a top-of-the-line modern GPU is still waiting for its very first clock cycle to even begin. This represents a fundamental paradigm shift. A silicon CPU is an active device. It eats power, it generates a ton of heat, which is a massive problem for an implant. This diffractive optical neural network, or DON, is passive. The computation itself uses zero energy and creates no heat. It's a cold processor. And this is the core concept you really have to wrap your head around. This isn't a computer that runs software in the traditional sense. It's a static, solid-state crystal. The logic, the AI's weights, they're not stored in memory. They are physically 3D printed into the very structure of the crystal itself. And this just illustrates perfectly how it works. A single photon, which represents your query, enters the crystal. As it travels through all these incredibly complex 3D printed layers, the light diffracts and interferes with itself. It literally performs a massive matrix multiplication on itself, focusing the resulting light onto the correct output sensor. The computation is just an emergent property of the physics. So how do you even build this? It's fabricated using something called two-photon lithography, which is basically nanoscale 3D printing. And that's absolutely critical, because unlike old-school 2D chip etching, TPL lets you encode logic through the crystal's entire volume. You get volumetric computation, which enables this immense parallelism. And the whole architecture is built to scale. By using different colors of light, something called wavelength division multiplexing, you could run hundreds of different neural nets in the exact same physical crystal, all at the same time. Okay, so we filtered intent with a chemical gate, and we've computed a result at the speed of light. Now we come to the final, crucial piece of the puzzle, closing the loop, getting that answer back to the brain safely and effectively. And this is a really critical engineering question, right? A lot of previous BCI tech failed right at this point. They caused long-term damage simply because of how they delivered signals back to the neurons.
So the crucial point here is this engineering leap. Older BCIs used what's called Faraday current, basically pushing electrons directly into brain tissue, which is toxic and causes damage over time. The NPA architecture uses ephaptic or capacitive coupling. It's a non-contact stimulation. No current ever touches the neuron. And would you look at that? That same ALD glass skin we saw in the input gate is back, playing a brilliant dual role. It's not just a protective barrier, it's also the perfect dielectric for a tiny capacitor. The optical output creates a charge, that generates an electric field across that ALD layer, and this safely induces a voltage change in the target neuron, causing it to fire, all without any toxic current injection. Now, the psychological effect of this is a key part of the design. Because the signal is delivered in this non-contact, capacitive way, it bypasses your normal sensory organs and integrates directly at the cortical level. The result is what they call an endogenous insight, a solution or a memory that feels like it just popped into your head. It feels like your own thought. And the final piece of this physical interface is just as elegant. To make sure there's a stable, solid connection for the long term, the device itself is built with this porous, honeycomb-like structure. The pores are sized perfectly, about 5 to 10 micrometers, to actually encourage your neurons to physically grow into the device. So the computer isn't just an implant, it becomes a structural lattice that your brain literally integrates with and inhabits. So let's just do a quick recap of the 3 foundational engineering innovations here. First, you've got the chemical gate, which brilliantly repurposes a material instability to act as a high-fidelity biological filter. Second, the optical accelerator, giving us passive, zero-energy, volumetric computation at light speed. And third, the capacitive feedback loop, which delivers a safe, non-contact signal that's perceived as your own thought. And that brings us to the final thought. For so long, we've been debating the dangers of artificial agency. This architecture just flips that whole script. It's about augmenting human agency. So the real question becomes, if you could eliminate that information bottleneck, if you could process reality at the speed of light, what currently unthinkable problems would you choose to solve?